Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. I'm going to go back and redo some of my older lectures that I did a long time ago in order to bring in some of the some good stellarium and good simulations to kind of help us understand things. And the first thing I'm going to look at here is the celestial sphere. So let's understand what the celestial sphere is and how we can visualize it. Well, first and foremost, we have to remember that we live on the Earth, and the Earth is spherical. It is a ball. It is a huge ball orbiting in space, and it's orbiting the sun at some distance of 93 million miles away. And if we turn around, we can see that it's over there. And we see that on one side of the Earth, it's illuminated by the sun, and the other side is in shadow because it's facing away from the sun. And the Earth is not flat. It is a ball. It is spherical. So as it rotates, whatever's in the sky is different for different people. So if we look at if we just look at, say, on this side, we see for the demarcation between night and day as it goes through sunrise. Now the simulation, of course, is kind of having some trouble here, but whatever. We can see that if we look at nighttime side, we see that as the Earth rotates, the position of the continents, and therefore anybody on them, changes with time. And so therefore, things that are in the sky change with time. So it's not like that the sky doesn't change. In fact, in some ways it does. In a lot of ways it does. But from our perspective, we see the Earth and we perceive the Earth as not moving. However, it is rotating on its axis. And as it rotates on its axis, what we see in the sky appears to change. It's exactly the same thing as if we were driving in a car and we feel like the car is not moving because it might be going straight down a long road at like 90 miles an hour if you're going really fast out west. And all of a sudden you're looking outside and you see everything zipping by you. So you know that you're moving only because you got in a car and someone's driving that car. But if you didn't notice that, or maybe you were on a train, the train appears to be still with respect to you. And if it's a really, really smooth track, then the outside world appears to be rushing by and you seem to be standing still. And that's the effect that we're having on the Earth. The Earth rotates on its axis, so therefore we see the sky move. So from this simulation, we don't see the sky move. But let's actually go and check out what we can learn about looking at the nature of our solar system. And I'm going to go look at the various, look at the grids, and I'm going to turn on the celestial equator grid, turn on the, well, not just yet. I'm going to look at the solar system coordinates, and I'm going to show the surface labels and the name and the grids and the axes. So the axis of the Earth's rotation is this stick that appears to be sticking out of the North Pole and a stick that appears to be sticking out of the South Pole. That is a line that goes through the center of the Earth, an imaginary line upon which the Earth appears to spin. And so that's called the Earth's rotational axis. There's also another slight little axis that's in tiny glowing marks, and that is, well, I guess if we pitched it just right, we hope to see that 23.5 degree tilt. But really, the Earth's axis is pointed. It has its own rotational axis, and there it is. And we have a series of grid lines, and those grid lines are latitude and longitude. The red line going across the middle of the Earth, right across the middle through Africa and through and across South America like that, that is the equator. And the Earth's equator is at what we would call 0 degrees latitude. And if we go up to the North Pole, it would be 90 degrees north latitude. Now, if we go around, we also see there's a special set of longitude lines which go from the North Pole to the South Pole, and those longitude lines show the position on the Earth's surface. That red line that runs through Greenwich, Connecticut, demarks the beginning of the coordinate system for latitude and longitude, for longitude specifically. And everything to the east is larger in longitude, and everything to the west of that is less than longitude. So our natural thinking is that imagine that we took the grid of latitude and longitude and extended it out into space. If we did that, we would be using what are called equatorial coordinate systems. So the equatorial coordinate system is an analogy of the Earth's latitude and longitude out into space. And if I line them up just right, you can see that the Earth's equator, which is the red line, directly corresponds to the celestial equator, which is now bright. So I'm going to brighten and dim it and brighten and dim it. And the celestial equator is the bright line that goes across the middle of the field. I'm going to zoom out just a little bit. The middle of everything in the sky. This is a grid that's on top of the sky. So we can think of I'll show you why we're even doing this in just a second. But the celestial equator is the imaginary extension of the Earth's equator out into space. Now, if we look straight up from the North Celestial Pole, from the North Pole, where that line seems to be pointing, and that line points at what we call the North Celestial Pole. So that is the NCP, or North Celestial Pole, and there's also a South Celestial Pole where the southern Earth's axis points towards, which is the South Celestial Pole. Now, there's also there's also a path upon which the sun rides, and that path is called the ecliptic. So the sun and roughly all the planets appear to ride on the ecliptic, which is a path in the sky. So if we were to watch the sun over the course of a year and see where it is in the sky, we would see that it's roughly on, well, it's always on the ecliptic, but the planets themselves would be roughly close to the ecliptic itself. So we have this interesting coordinate system which is on the stars and is an analogy with respect to the Earth's latitude and longitude. But notice how the Earth, as it rotates, latitude and longitude go with it, but the celestial equator does not change. So now, if we look at it slightly differently from a relative point of view, and we go onto the surface of the Earth, then we see a completely different appearance. But I just wanted to make sure you understood that we have these coordinate systems which can be thought of as extending out into space. Now, the latitude-like lines in the celestial equatorial coordinates are called declination, and the longitude-like lines in the celestial sphere are called right ascension. And so if we click on, say, some star or something, we will get the information about that star, and it'll show what its latitude and longitude are. Specifically, its right ascension and declination. So that's interesting about those particular things. And notice that the latitude and longitude are fixed on the Earth, and the celestial coordinate system appears to be fixed on the sky. So the sky is not the limit, but you can think of it as a grid that is superimposed in front of or along with the stars. And why do we call it that? This is this imaginary concept called the celestial sphere. And I'm going to turn off the ecliptic for this purpose. But the celestial sphere is an apparent sphere that surrounds the Earth. And appears to be above, below, and all around the Earth. And what it appears to be is a grid or coordinate, or the apparent feeling that the sky is a grid or a sphere on all above us, upon which the stars and planets appear to move. And so that's actually a pretty interesting way of thinking about it. But let's actually now dive in deep and go take a look at a different way of looking at it, which is a different piece of software, which is called Stellarium rather than Sky Safari. I'll close that off. And so now we're looking specifically at the, hold on, let's zoom on out. So now we're looking at a software called Stellarium. The other was called Sky Safari. And we're looking at roughly today's time and date. And if you look, we see the sky above us and around us, and we can determine two different coordinate systems on the sky. And the first coordinate system we're going to talk about, again, is what we call the equatorial coordinate system. And there's the equatorial coordinate system we saw before, but now on the sky as though we're looking at it from the ground. So if we look at it as though we're looking at it from the ground, and we face, say, south from, say, somewhere in New Jersey, I'm just going to speed up time a little bit and watch what happens. Because now the Earth is rotating, the celestial sphere, or the celestial coordinate system, the equatorial coordinate system, appears to move in the sky. But remember that the celestial coordinate system is in front of the stars, which themselves don't move. So if the stars don't move, then what we have is we have a series of grid lines that are in front of the stars. And so the stars themselves appear to be attached to the grid lines, or at least as deep in as we want to go. We can go in as far in as we want. That's a little crazy looking, so let's slow things down, nice and slow. So you can see that individual stars, maybe those are like moons or something that are zipping by, or asteroids, or actually probably just satellites, Earth satellites. So we have objects that are on the celestial sphere that are enmeshed inside of this grid that we call right ascension and declination. Up and down on the celestial grid is declination, and left and right is right ascension. So if we then zoom way back out, we're getting close to 4 a.m. and that's getting close to sunrise. And as the sun rises in the east, we see the grid slowly moving with it. There's the constellation Orion rising in the east in early August. We don't see it because the sun is close to it. But notice that as the stars rise in the east and set in the west, we actually look at this object that we call the celestial sphere, and these grids are for it. So why do we use this? What's the purpose? Well, it's to help us find our way around the sky and find things in the sky. So what I'm going to do now is that as the sun goes up, I'm really right now interested more in the locations of the stars rather than the sun. And the sun's very interesting, but I'm going to turn off the atmospheric effects of stellarium, so it allows us to always see the stars. And so I've done that for a purpose, and the reason is I want to actually look at how the effect of the celestial sphere has on the motions of the stars in the sky. So notice as we look at these objects, everything does appear to rise in the east. But when you say rise in the east, what do we mean? It doesn't rise straight up, does it? The stars aren't going straight up. They're going off at an angle. And what angle is that? They follow the grid lines. In fact, since they're attached to the grid lines just seem, they're not rising, they're not going straight up, they're going off to the side. So as the stars move, they follow the lines themselves. And in fact, they follow the declination lines, which are going up and to the right, are the lines upon which we can see things moving, or at least that is the apparent motion. Now the the lines that are going this way, the right ascension declination lines, those lines are the ones that demark how long it will take for it to move from one point to another. So if I just let my mouse sit there in one location, we can see that star actually approaching. I think it's not actually a star, I think it's a planet. Yes, it's Mars. So we can see how Mars will move with respect to the sky. And so if I place my mouse there, and because the distance between two of the lines is 10 minutes of right ascension, it takes 10 minutes of time for Mars to span one box length on there. So that's what those things mean. All right, but our key thing is that let's actually now see what we mean by approaching the stars, and maybe this will help. I'm going to turn on the constellation lines to kind of keep things moving. And notice that the constellation Leo over here, Leo the Lion, which is this one here, Leo the Lion stays fixed with respect to itself. The stars are not moving with respect to the grid, nor it is in the river, nor it is in any other constellation. The stars themselves do not appear to be moving with respect to the constellations. And that's important to know, because when we actually do look at the nature of the stars, we want to know, I don't want the calendar up, we want to actually see how they behave when they rise in the east and set in the west. There's the moon coming up, but notice that the stars appear to be moving up and to the right when they rise in the east. If we look towards the south, there's our meridian line. Again, I turned it on, and we turned and the meridian line actually tells us a very interesting thing about the nature of the equatorial coordinate system, because the meridian line goes from due south to the zenith overhead, and then all the way to due north. So let's actually zoom out to see what I mean by that. So there's straight overhead and then down to the north. And notice what an interesting thing is that since we went straight overhead, we now see that the north celestial pole, which is towards the north, actually does not move. So the north celestial pole We can spin time a little bit faster to see what happens. And as it kind of dizzies around, we see there's the North Star, or the star Polaris, which is in the constellation Ursa Minor. In fact, I'll turn on the constellation names just for enjoyment purposes. There's the constellation Ursa Minor, which is the Little Dipper. And so you can see what I mean. There it is. The Little Dipper is moving. And the North Star does not appear to be moving with respect to the North Celestial Pole. So now notice I've sped up time, so many minutes are going, about an hour is going by every few seconds. So we can see that as the stars rise in the east and set in the west, there are some stars that are pretty special, like all the stars of Camelopardalis, and the stars of Ursa Minor, and the stars of Cassiopeia, and the stars of Cepheus, and some of the stars of Ursa Major. They never set. So notice that the stars of Ursa Major, the Big Dipper particularly, look how low it gets to the horizon for people in Wayne, New Jersey. It never gets below the horizon. Such stars are called circumpolar stars. The stars of Ursa Minor are circumpolar. The star Erai in Cepheus is circumpolar, meaning they go around the North Celestial Pole and they never set. So let's turn the grid back on to see more interesting stuff. So there's the North Equatorial region, and now we go and look due west. And as we see things looking due west, we see the constellation Taurus coming at an angle. And what is the angle with respect to the horizon? If we look due west and go straight this way, make an angle from the horizon up to the celestial equator, this angle between the celestial equator and the horizon at due west, or 0 degrees, the celestial equator is here. What we see, let's see if I can turn that on. No, that's the ecliptic, and maybe where's our celestial equator? Okay, let me see if I can find it again. There it goes. But in any event, we see that, oh, I think I lost it. We have the angle between the celestial equator, which is here, which is 0 degrees declination, and the horizon is equal to 90 minus the altitude of the North Celestial Pole. Well, what do we mean by altitude? Well, for just a second, let's turn off the equatorial grid and turn on the azimuthal grid. Now, the azimuthal grid shows the position of the stars with respect to the horizon. Now, this is your perspective that you see on the sky. So this is a grid with which the stars are moving according to. But now, what do they move? They say, well, each of the lines from the horizon up is a few degrees of altitude. So if it's at the horizon, it's 0 degrees altitude. There's 5, 10, 15, 20 degrees above the horizon in altitude. We can go as high as we want, but as soon as we get all the way to straight overhead, we see straight overhead is the zenith. And the zenith is the place that is directly overhead. That's what we call the zenith. And you can see that all of the altitude lines kind of go all the way to the top. And there goes the stars of Hercules are about to pass through the zenith. And we see that there's also this other line, the meridian line. And the meridian line says, let's say we go to the right. So this is 5, 10, 15, 20 degrees to the right, all the way around from north to east to south to west to northwest and back. And so that is called azimuth, and your azimuth angle is how many degrees from north to the east you're looking. So we can find things in the sky if they're going at a normal rate, like normal rates, like this is like normal 1 second per second, then things don't move very fast. However, they move fast enough so that the altitude azimuth system doesn't work over time for showing people things. Also, it doesn't work if you're looking for things that if you're trying to tell a friend in another location to go look for something. So let's say there's something really interesting happening right now on August 7th at 3 o'clock in the morning, and you want to tell somebody that's very far south of you what to go look for. So right now at 3 o'clock in the morning, maybe there's a star that's exploded or something. Maybe there's a supernova that's happened. There's a Milky Way in the background, so maybe it happened. So we're going to say, your friend says, wow, what's happened with the star Deneb? something is flaring or something happened in Deneb, or maybe you just want to point out the star Deneb for your friend. And your friend, say, lives in a different location on Earth. Maybe your friend lives very far north, really far north, almost to the northwestern territories of Canada. So you tell them to go outside and look, and wait a second, something's different about that. Notice what happened. The star Deneb is now very, very, very far north. And let's see if I can find, or at least there it is. You can see it has a totally different location on the sky. So the star Deneb is much higher in altitude than for people that are here. It's also got a different location in the sky for the horizon as well, because of their different position on the Earth. So Deneb has a much higher altitude, but if we go very far, let's say we go all the way to the north end of Greenland, notice that we're way up north, very far north, even farther. Let's go all the way as far north as we dare. And if we go north, 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 and maybe we go a little bit further back west or something, let's go see if we can push it back. Notice that as far north as we are, we actually don't see too much difference. So actually, there we go. Let's go farther south in our altitude. Go back over to New Jersey, and there we go. Let's actually just go straight north from New Jersey and see what happens. Interesting, huh? Notice how we go straight north, and the altitude of Deneb has changed. But actually, let's now take a more interesting look and go all the way over to the Little Dipper. So there is our favorite star, Polaris. So Polaris is here, and now we're very far north, but let's change our location on the Earth, and we'll start here, somewhere in in the middle of the United States, and then what we're going to do is travel northward. And as we travel northward on the United States, we see that the North Star, it gets higher and higher and higher off the horizon, until we finally get all the way very, very north, 80 degrees north latitude. What's going to happen when we get above 80 degrees north latitude? All right, there we go, 75, 80 degrees north latitude, keeps going up, up, and finally, once it gets to 90 degrees north latitude, that is the North Pole. The North Pole is 90 degrees north latitude, and when you're at the North Pole, things look really different. So let's close this out for just a second. And I'm going to just actually let time go a little faster, and we'll see what happens. So I'm looking what looks to be south at the North Pole, but if I just kind of let time go, notice how what are the stars doing? They don't rise, they don't set. They actually stay at the same altitude. None of them are rising. And even interestingly, I'm going to tag the sun and follow the sun around. As I follow the sun around, notice how it's going around the horizon, and every direction is labeled S for south. When you're at the North Pole, there is no other direction but south. There is no east. There is no west. There's not even a north anymore. When you're standing directly at the North Pole, the only direction is south. And notice what's happening with the sun. It's neither rising nor setting. All of the stars, they just keep orbiting. And that's because when you're at the North Pole, your horizon is directly below the axis of the Earth's rotation. So nothing can rise or set because of your latitude. So let's actually take our trip, and we're going to go back south again, and I'm going to reduce our location. So let's go back down south a bit. So boom, 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 boom. Now I better stop doing that. I'm going to fix my location. I'm going to look due north again and go back in here. And here we go. Let's go down south. And as I go further and further south, we see that the stars that are circumpolar are fewer and fewer. And so now that's roughly our latitude, my latitude in New York City. And let's keep going further and further south. I'm going to take it all the way down to, say, the southern tip of Florida, which might be 29 degrees above the equator. And let's keep it going further. If we go below into Cuba, it's about 25 degrees. If we go all the way down to, say, we're looking roughly in the Panama area. Panama might be only 11 degrees north of the equator. And so notice what happened with the North Star. The North Star is really low to the horizon. And so we keep going lower and lower and lower, and watch what happens. That's interesting. So let's descend, 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 descend until we get to the equator. So now if we're at the equator, we have another interesting thing that occurs. Notice the north celestial pole is on the horizon. The stars go straight overhead. But now we got something very interesting. Let's look east. Due east. Remember in New York City area how the stars rose at an angle to the horizon. But at the equator, they rise straight up from the horizon. Everything, when it reaches the horizon, raises straight up. Isn't that interesting? So look at everything going straight up from the horizon. Now, as you go further and further south, when it rises off the horizon, that curve just goes immediately turns it. But if we're looking due east, the stars rise directly up from the horizon. The angle that these things also do is the same, but if they're on the celestial equator, they will not veer left or right. Notice as we look further and further south, now we see something interesting. There are constellations that you're probably not familiar with. Musca, Chameleon, Volans, Dorado, Mensa, Reticulum, Crux. That's the Southern Triangle. Circinus, Lepus you might know, Pupus you might know, but these are all stars. There's Scorpius there. Now Scorpius is interesting. It's very, very, very low in the horizon for us down in the in New York City. But when you're at the equator, it can get very high off the horizon. Look how high that is. It's getting up to 60, 70 degrees off the horizon. So if you're on the equator, you get a good chance to see the things in the center of the Milky Way, which is really beautiful. All right, so when you're looking south, we see that the south celestial pole, or where everything seems to be rotating around, is there. And then we go look at the west, and we see things again descending straight into the west. Now let's try a little game. We're going to look to the south this time, and we're going to continue our walk on the Earth south as I change the location of our direction on our location on Earth. I'm going to continue going south, and notice what's happening. I'm going to keep going south, and I'm going to stop in just to like 30 degrees south. So now I've gone 31 degrees south. Interesting. That's like looking north from 30 degrees north, except now we're looking south. So let's see what's happened on the rest of the celestial sphere. We see this whole thing. We now understand the nature of right ascension of the altitude and azimuth, showing how things rise and set and their altitude off the sky and their direction around the horizon. But I'm going to bring back the azimuth, the equatorial grid. Now, last time we looked at this from the equatorial grid standpoint, we were looking north, and we were looking to see the North Star. But now we're looking south. So we're seeing the south celestial pole. The south celestial pole is the place around which all stars in the southern hemisphere appear to rise and set. So I'm going to go a little further south. Let's go to 40 degrees south just to have a little bit of fun. But the problem is that there really isn't a North Star of the South. There really isn't. I mean, there are stars, of course, that are nearby, but they're very, very faint. This is a very faint star of magnitude 7. That's a magnitude 8 star. There are really no truly bright stars that are close to the south celestial pole. So what people do instead is that they use, in the southern pole, they use the constellation Crux, or the Southern Cross, to point at the south celestial pole. So all you have to know is the angle between these stars and the south celestial pole, and know how far off you got to kind of joggy it to get there, because it's not pointing directly at it, is it? You can see that that's pretty clear. But the Southern Cross points roughly at the south celestial pole, and so that can give you your latitude. In fact, your latitude is the altitude of the south celestial pole or the north celestial pole off of the horizon. If it's the south celestial pole that you're looking at, then you have a negative latitude, or a latitude below the equator. If it's north, then it's the other way. So now let's go look to see what happens when stars set in the west. This is different. The stars, when they set in the west and the south, say in Australia or South America or Southern Africa, notice how the stars appear to set from the right. The angle that they make to the west is originating from the upper right to your upper right, and then they go down to the lower left. So the stars themselves are kind of seen backwards in how they rise and set. And some familiar constellations are upside down, like Scorpius and Sagittarius and Aquila and Corona Australis. There are all these constellations that we're very familiar with that are now apparently upside down according to Northern Hemisphere observers. Well, let's look for the North Star. If we look for the North Star, we're going to be out of luck because the North Star is below the horizon. And we can't even see the North Ursa Minor, the Little Dipper. And even still weirder, there's Orion, which is now upside down according to a northern observer. There's Gemini that's going there, Taurus, the bull, and the sun is, of course, moving across. So I think we can bring back the ecliptic just for enjoyment. There's the sun passing along the ecliptic. And the ecliptic itself is fixed with respect to the stars, but we'll turn that off for now. Actually, yes. So we have Leo, the lion, upside down according to a northern observer, but that's just fine. But notice we cannot see the North Star. There are no circumpolar stars to the north for southern hemisphere observers, but there are circumpolar stars to the south for southern hemisphere observers. And notice stars in the southern hemisphere, they rise in the east, but they go in the upper right. So your latitude is, of course, the altitude of the southern celestial pole, and that's whatever latitude this is, that would be about 40 degrees off the horizon. Again, if we wanted to play the game and go all the way to the South Pole, we can do that. And if we do, we have to go all the way down. Let's keep all the way down to the South Pole. Let's go all the way down. Let's see how fast it takes. I'll keep clicking until at 81, 82, and then we're at the South Pole. Again, at the South Pole, nothing rises or sets. So if you're down there in the winter and the sun is below the horizon, you have 24 hours of night for 6 months. So the sun never rises for 6 months. The day is 6 months long at the South Pole. The night is 6 months long at the South Pole. The same with the North Pole, which is really fascinating. Either it's day or it's night there, and there's no rising or setting of the sun. All right, let's take it back to our normal location and bring it back to our default location, which is in North America, roughly New Jersey. And if we look south, we don't see the South Celestial Pole, and there's Scorpius back in its normal place for us New Yorkers and New Jerseyers. And where we go, we look to the west, we see it kind of setting in the way we expect it. So then we go back over here, and there are a number of things that we can chat about again. But most important thing is, as we look out into the night sky, we see that this thing called the celestial sphere exists. And so what do we do with that celestial sphere? Well, first let's turn the time to a normal. And now I'm going to go all the way over here, and I'm going to say, we'll look at the constellation Lyra, Lyra the Lyre. And I'm going to zoom in on constellation Lyra, and I'm going to go all the way over to a famous double star, which is Epsilon Lyra, the double Epsilon Lyra. And if we look closely at its coordinates, we see RA and DEC, 18 hours, 44 minutes, and a declination of plus 39 degrees, 36 minutes. But why does that matter? Because if we go back and turn on our equatorial coordinate system again, we see that that is the exact coordinates of Epsilon Lyra, or let's just stick with Vega, because Vega is easy to find. Vega is one of the brightest stars in the sky. So Vega is a very, very bright star with a right ascension of 18 hours and 36 minutes and 56 seconds. So 18 hours and 36 minutes means this is the line for 18 hours and 35 minutes. There's the hour, and there's 18 hours and 36. And if then what's the declination? The declination goes up this way until we get to 38 degrees. So here is declination 38 degrees. Here's declination 39. This is 38 degrees and 47 arc minutes. So because the coordinate system, the equatorial coordinate system, is fixed with respect to the stars, Vega's right ascension and declination does not change, even as its altitude and azimuth change. Notice the altitude is changing and the azimuth is changing. That's because as the Earth rotates, the altitude and azimuth change. They must change because the height off the horizon is changing. And accordingly, where it is along the sky up from the horizon changes as well. But the right ascension and declination is fixed. So we have a longitude and latitude on the Earth, and we can think of the celestial sphere, which is an imaginary sphere above us, covered with a coordinate system called the celestial equatorial coordinate system that is fixed with respect to the stars, and we can think of the stars as put on a big celestial sphere, which is of course imaginary, but that helps us to do a coordinate system, and that tells us where things are in the sky. So we can use altitude and azimuth. That's very helpful for observers on the ground, but the right ascension and declination is really good if you want to know really where something is, and you want to tell somebody where it is also. Be that as it may, let's actually change it. Let's show you what I mean. So now I'm going to change the location. I'm centered onto Vega, and now I'm going to change my location to somewhere further west, say out in Colorado. If we look at if we go out in the west, we see that it seems to have rotated, which seems like things have changed, but notice that the altitude has changed and the azimuth have changed, but the right ascension and declination have not. So the altitude here and the azimuth here have changed, and if I go to, say, Mexico, definitely the altitude has changed and the azimuth has changed. If I go up to Canada, the altitude has changed and the azimuth have changed, but the right ascension and declination have not. So that coordinate system, right ascension, declination, and equatorial coordinate system, is perfect for telling people exactly where to look, because you don't necessarily know what somebody else's altitude and azimuth are for, say, Vega. That actually helps us find where things are in the sky, and that's their important things. So you would go out to a friend, and you might just say, well, look above the horizon and look for that bright star. That's going to be kind of difficult, because they might have it in a different location than you. In fact, look how different it is to go from northwestern Canada to New Jersey. It's radically different. So the place in the sky for Vega is very different for two people on Earth. And that's because the Earth is a sphere, and because it's a sphere, different observers have different locations that they can look at. So this is an introduction to how we find things in the sky, and what we're actually looking for when we go hunting around for stars in the sky. And we can see that the stars themselves are fixed with respect to a coordinate system that we call the equatorial coordinate system, and that helps us navigate the sky on the celestial sphere.